Hello everyone, this is Zheng Ye from Utah State University. This presentation has been given to the SDM meeting in 2011 in Denver. The topic is a new approach to bonding effective properties of random heterogeneous materials. The motivation of this work comes from the fact that more and more structures are made with random heterogeneous materials to achieve better performance. Because of micro-level complexity, it's both time-consuming and unnecessary to analyze each detail inside the material to anticipate the overall reaction. Variation asymptotic method for unit cell homogenization, which is VAMUCH, has been demonstrated as an efficient method for periodic deterministic heterogeneous materials and used by hundreds of researchers and some companies such as Hair. The goal of present work is to expand this method to bond random heterogeneous materials and add a new ability to VAMUCH code. What is homogenization? From the left picture, it is a heterogeneous material composed by matrix and some reinforcements that the material properties are different from one another. The purpose of homogenization is to replace the heterogeneous material with a homogeneous material and calculate its effective material properties. The mathematical explain of homogenization is microstructure details become very small and can be homogenized when we stand outside to micro level. The reason we can use rigorous bounds to describe random heterogeneous materials are listed below. First, they give the constraint of effective properties. Second, they become progressively narrow when more deterministic microstructure information is provided. The third reason is that one of the bounds usually can provide relatively accurate estimate of effective properties. The first reason is that they give the clue that how to choose different phases under the inclusions of microstructure in computer simulation or in experiments. For brief background, I list some of the main existing methods here. Void bounds, which is a arithmetic mean of all the material properties, give upper bound, and Ruther bound, which is a harmonic mean of all the material properties, give lower bound. The Hutchins-Strachman bounds is known as second-order bounds because it includes the two-point correlation functions, and the third-order bounds is using three-point correlation functions. The higher order, the more information provided from microstructure and leads to narrow bounds. But it is hard to get n-point correlation functions when n is larger than 3. The weakness of current methods are the upper bound and lower bounds do not get converged when the realization becomes deterministic. The second is that they need different form of correlation functions to integral according to different situations. The third reason is that they base on statistic homogeneity and isentropic assumptions. The first reason is that some of them are not narrow enough for lower order. The last reason is that the endpoint correlation functions is numerical and experimental difficulties to calculate. In this flowchart, it is a three-step procedure to get the bounds. The first step is to get a large number of realizations to form stochastic unit cell, which is known as SUC. Here, a large number means we get enough microstructure informations to assemble a unit cell which contains stochastic information. The second step is to calculate pointwise expectation material properties using Monte Carlo method. With those information, we will use variational and dual variational method to get upper bound and lower bound respectively. From this picture, it shows how to get stochastic unit cell. In a random cell structure, or it is called shaking geometry in literature, the inclusions are randomly distributed inside each unit. When we use all of those informations to assemble a stochastic unit cell, it contains all the position possibilities and can be used in analysis. Then the pointwise expectation material properties can be calculated from the stochastic unit cell. In numerical approach, Monte Carlo simulation is used to create stochastic unit cell, and the expectation material properties for certain point can get from the mathematical expectation. In experimental approach, samples are gathered in to form the stochastic unit cell, and the rest of the procedures are the same with numerical approach. For the upper bound, expectation of stiffness matrix needs to be calculated. On the other hand, the transverse of expectation compliance matrix is needed in lower bounds. Let's take a two-phase porous material to demonstrate how this works. A porous with radius r is randomly distributed inside a square unit cell. We assume the properties of porous is 0 and the matrix is 1. For each realization, the point material properties related with the distribution of porous and can be described as following equation. In the right image, for the radius equals 0.29 and 0.33, we use 100 Monte Carlo simulations to calculate expectation material properties, and shows below. Compare 100 and 500 Monte Carlo simulation with analytic solutions at the surface cutting through the longitudinal. It shows Monte Carlo simulation has the ability to catch expectation material properties. Now we are moving to a theory part to see how to use expectation material properties to get upper bound and lower bound. For the upper bound, the effective material properties for realization, omega, can be obtained by minimizing the following functional, considering the periodicity of chi I. This functional represents the strain energy inside a unit cell with volume omega. Apply mathematical expectation on both sides. We use C bar star to express expectation of effective properties of all the realizations, and can be expressed as following. Please note the minimization can be moved from expectation if chi I takes arbitrary function of variables. If we choose trial field of chi I remains the same for all the possible realization in the functional, the equation becomes an inequality as follows. And this can be solved routinely by VAMUCH and leads to the upper bound. To find the lower bound, the joule of strain energy can be calculated using double Young-Fench transformation. Because the strain energy is convex and continuous, L star star equals L, the minimization of dual variational problem for realization omega can be formed as this equation. According to inequality here, we can get max out of the integral, and changing the order of max and minimum, we have the inequality as this. Using integral by part and the divergence theorem, the inequality can be simplified to this equation. Applying mathematical expectation on both sides, we can get the second equation. We can also further select the trial function sigma ij to be this form and put in dual variational form. The inequality becomes this one. Denote following matrix form, the lower bound can be calculated as this form. To show the power of approaches, we apply them to two problems and compare the results with the literature. The first example is fiber-reinforced example. We didn't compare the result with void and rooster bounds because the bounds is already shown as the worst in the literature. The results of Hauschen-Streckmann and third-order bounds are compared with VAMUCH bounds. The proposed problem is a two-phase material with volume fraction of fiber from 10% to 70%. The material properties for matrix and fibers are isentropic, and the Young's modulus and the Poisson's ratio are listed below. Here it shows the result that the bounds of the longitude shear modulus and transverse shear modulus. For the lower bound, those three methods give similar results, and for the upper bound, when volume fraction becomes high, the VAMUCH result shows improvements than the other two because it's narrow. Here is our 3D example and its isentropic situation. It also shows the experimental results fall in the VAMUCH bound, but it falls out of the third order bound. The unique feature of the new approach is that it can catch the bounds changing with respect to the changing of variance. In those figures, we can see the variance of random position decrease from right to the left. Plot the results of upper bound and lower bound get from the VAMUCH. It shows it converges to some deterministic results, as shows here. The same test also carried out with two-point correlation functions. With different variance, it shows almost no difference, which means the upper and lower bounds based on endpoint correlation functions cannot catch this kind of characteristics in homogenization simulation. Finally, as a conclusion, my original spectroscopy method for unit cell homogenization was extended to bound effect properties of random distributed heterogeneous materials. Point-wise material properties averaged all the possible statistical realizations are first obtained by Monte Carlo simulations. The new approach to get expectation material properties is more efficient than getting endpoint correlation functions. The new approach naturally bridges the effective material properties of deterministic heterogeneous materials and the random heterogeneous materials. And it is systematically derived and it is general purpose. Here I will end my presentation, and if you have any questions, you can send me an email. Thank you.